So I'm going to just use a couple minutes, going to go ahead and let people keep coming in. Through another just a little demo we're running in our booth, and essentially this talk's going to include some network performance tuning. And so kind of what you're seeing here are network latency tests. And I don't know if those doing networks, so usually performance, you like to see the bars higher or faster, etc. Latency is just the opposite. And a fundamental thing that we really want to do, and you see the middle sections here, is when we enable our TuneD network latency profile, is we really want the patient to be dead here. Total flat line, no disruptions, ultimate determinism. So while it's not completely real time, it's can be tuned very close to real time. And so Jeremy Eder is on the right. He's going to be taking us through the network performance. Larry Woodman is on our virtual memory again. And I'm Douglas John Shakshober. Shak is my nickname. It's much easier. And one of the things we thought we'd do, there's a couple questions. One of the top questions was,
where can I get the slides? Customer portal in a couple of days. Second one, what would be a real-world application for groups? I assume that means C groups. We put a slide in the first deck about how libvirt and Docker both use the C group subsystem to do resource management. Those are the real-world use cases. Third question is, what is the slit? Shaq, you want to take that one? Or Larry?
The
slit table, I think, right? Yeah.
Yeah. Was it the system location in I forgot what the acronym stands for. Basically, it is the table that the BIOS writes into memory that describes the memory, the NUMA nodes, the CPU enumeration in the NUMA nodes. What else is in there?
Yeah, it's just a representation of the hardware config, the BIOS information as it's passed to the operating.
Like a system location information table.
System locality.
System locality information table. Yeah.
And in fact, IRQ balance. We showed you LS topo. They read what the BIOS presents. So we've actually had some prototype systems where the slit was wrong, and the tuning or the performance we got was off because of it. And so we provided that feedback to the vendor.
Right, and they actually at boot time the kernel reads the slit table and builds basically builds the nodes, or the NUMA nodes, data structures, and then all the CPU data structures and so forth that are enumerated from that slit table. And like Jeremy said, there have been issues or times in which the slit table was wrong. Specifically, the enumeration of CPUs in the slit table was wrong. So the kernel thought that CPU X went with node Y, and that was not correct. And it's pretty obvious that the performance.
It's pretty obvious, yeah. I mean, we showed you. We have some slides coming up, so I won't do the big reveal now. But and the last question is TuneD available for RHEL 5?
No.
Right. So
but TuneD is a profile delivery mechanism. All it does is roll up tunings into a consolidated place. It allows you to roll them out, roll them back, change between profiles at different times a day. So in reality, it's just an automation mechanism. You can write your own sort of thing. We do have Ktoon, very nascent version of TuneD and RHEL 5. So you can do roughly the same thing with all your scripts already. We're just trying to make it a little bit easier. Plus, we're also having products want to deliver their own TuneD profiles, like Rev. So that's it for questions. I think the app will allow you to send questions for this second part to a different iPad. So
yeah,
please do that.
And the other difference for the second part, as again, keep letting people come in as needed here, is at the end, rather than having people come up for questions, we're going to hopefully have a few seconds to do some questions, interactively here. But we will also kind of take the questions outside, afterwards, or maybe over toward our booth. Our performance booth is in the center section. So again, welcome to Red Hat Summit, and you're in the second session of performance tuning analysis. And so I assume you're here because you want to be. And so we'll get started again. First topic is disk I/O in RHEL. And again, so we're going to start out by recommending a TuneD profile for that when you are running RHEL 6. And RHEL 5 users, please try to just start the K-tune service. It's kind of a binary on and off, and it will do something similar to what we're recommending for disk I/O, which is throughput performance. And so if we look under the hood of what is changing, so if you do have chips that support CPU frequency, power saving governors, we're going to set it, instead of on demand, we're going to change that to performance. So performance profiles more aggressively will crank the clock speed up when you see activity on a core or a system. So by default it's on demand because, you know, various chip vendors and everyone wants your data centers to be green. If you do disk I/O or even network I/O, you don't necessarily put enough CPU demand to necessarily always ratchet your clock frequencies from, you know, say 1 gigahertz to 3 gigahertz, right? And so the performance governor, as soon as you see some activity, it'll ratchet that up and it'll help your I/O performance. Other things, important things, energy biases, and read ahead is another thing on the mounted file systems. It will check both the devices as well as the LVM devices, and we can actually, in a throughput mode, you're actually going to more aggressively do read-aheads, which on modern controllers usually almost always gives us pretty significant gains. Larry went through the scheduler changes. Throughput, so the analogy of throughput is, you know, how much data you can get through. We actually want our quantums a little larger and actually closer to what RHEL 5's defaults were, which is 10 milliseconds. I think I might have said microseconds last time, but no, we want to range between 1 millisecond and 10 milliseconds. And so a throughput wants to have more stuff done before we start doing a context switch, which is different than you'll see with network performance, latency. And then finally, there's 2 tunables on the bottom, and Larry's going to help step us through what these dirty ratios as well as swappiness parameters do in the VM when you're trying to push disk I/O, whether it's buffered I/O or even direct I/O, but mostly buffered I/O through the page cache and flush it out to disk. And so Linux's page cache is really key to a lot of I/O performance, and so we'll spend some time. So what happens in RHEL 6 again? The default scheduler for 6 is a completely fair queuing I/O elevator. So this is at the I/O level. It's not a schedule. I don't know if it's even they call it an elevator rather than a scheduler. So it's not really anything to do with the CPU scheduler. But the bottom line is a deadline scheduler on modern storage, enterprise storage, things that can absorb I/O at a reasonable rate, things with, it can still be spinning media, but it's maybe a stripe set or a fiber channel to a back-end virtualized storage or something like that. Deadline is preferred. It's been changed upstream now as the new default, and in fact in RHEL 7 the deadline scheduler is used. If you really do have ultra high-end SSDs, like backplane SSDs, etc., Fusion IO, whole variety, Verident, you name it, Micron, there's a whole slew of, a lot of their drivers actually will set the no-op, and that just means you're going to take some of the aggregation the kernel does to try to optimize the path from, and basically we can do things like the read-ahead and write gathering are 2 optimizations, and no-op literally doesn't do those because the device is so fast it's just a little extra overhead. So again, what do we generally get from this? So there's 2 different charts, and it's probably, the idea is you want to look at the difference between the bars, and each of them are a geo mean of about 14,000 data points. So it may seem like, oh, you're trying to represent all of I/O as this, but in reality we see a nice improvement, whether it's ext3, 4, XFS is also a new default in RHEL 7 versus ext4, and you actually see the relative differences to the same storage of the file systems. GFS2 is our cluster file system, and again, that does have some overhead because it's got extra metadata to perform the cluster operations, but in general, TuneD can give you a really nice gain on on a RHEL 6 system simply by setting a profile knob. Finally, picking a file system. So here's a preview of some comparisons between RHEL 6 and RHEL 7 for, again, the pair of bars that are XFS on the left. Now this chart is actually time of a real application, a SAS mixed analytic workload, and so lower is better in these cases, both user time and system time. And the difference between the distributions actually is shared as a percentage in the chart. And so you can see XFS has been working on, it's always been very good as a file system. We started supporting it in RHEL 6 tech preview early on, and then fully supported in, I think, 6.4. And EXT is our legacy file system, and we still have a lot of application developers there. It's scalable up to, well, XFS goes up to 100 terabytes for an individual file system. We certainly can do, you know, petabytes worth of storage mounted with different file systems, but that's a single max file. So if you guys have lots of 100 terabyte files you want lying around, I really should go work for a storage company. But no, the important thing for the OS is the ability to support that in a file system. EXT4 still goes to 16 terabytes, and EXT3, you know, only has a limit of 2 terabytes for a max file size. I should mention before jumping to that, so EXT4 in RHEL 7 has become the stock EXT file system. EXT2 and 3 actually have modes. They've consolidated the code, and in fact there's a slight degradation when you go to RHEL 7 for EXT3, and that's actually an implementation and a maintenance issue upstream, is that we probably are not going to be able to work on that to exceed that, because EXT3 again is really a legacy system with limited capabilities. But EXT4 and XFS are sort of the two primary ones. So we're going to go through this. I'm going to hand off to Larry at this point, but basically we're going to go through some of the architecture of the Linux page cache and the slab cache for the metadata, et cetera. And if you're ever doing benchmarking, the first and foremost suggestion, because Linux is buffering things into a page cache, and you run it once and it's slow. You run it again and wow, it went really fast. And it's probably because we could fit the files into memory, and you're actually testing the disk the first time, and the second time, after you've mounted a file system, at least the read portion is actually been brought into memory, so it can be 10 times faster. So please don't think you've found gold when you ran, I could just run my benchmark twice in this, I'm on, you know. Anyway, so the important thing is you can drop the cache or for both the data portion of the file I/O and for the metadata through these commands, and you can do them both with the final command.
Right.
So I'll transition to Larry.
All right, so before the break there, what I said what I was going to do is talk about some of the parameters that you'll see in the TuneD profiles. There's probably a couple extras that aren't in all, at least in all of the profiles. And I put them into 3 buckets of reclaim ratios, write-back parameters, and read-ahead parameters. So just before I even started here, the way what the page cache does is it uses memory to cache the file system data, not the metadata, but the data. And there's quite a bit of tunability in that. And how you tune that page cache gives you a real trade-off between throughput and latency. So this is just a picture that shows you when you actually are doing read-write operations, you're not going to disk at all, as long as you've got the thing tuned appropriately, and only 1 out of every n I/O operations actually go to disk. But this is what while introducing a lot of performance, a lot of throughput here. You bring a lot of data into memory, and when you write it back, you write a lot of data from memory back to the file systems and so forth. It's also what introduces the high latency. If you do absolutely nothing, you just sit there and read right in and out of memory. But when it's like a memory collector or something, and when the system finally has everything dirty and it needs to be flushed back, an operation that took a matter of microseconds can take 1,000 times longer or even more if it introduces a whole bunch of write back and so forth. So adjusting those parameters, once again, we don't have any parameters that, you turn this up to go fast, you turn it down to go slow. There'd be no sense in doing that. These are all trade-offs between throughput and latency. So this parameter swappiness controls how aggressive the system reclaims anonymous memory. It's set to 60 by default, and it isn't the percent or anything. It's just an integer. If you increase it, the system swaps anonymous memory more aggressively. If you decrease it, it decreases the aggression and then therefore reclaims the page cache more aggressively. It's set in almost all of the TUND parameters. It's one of the highest used ones. Basically, like I said, decreasing it, more aggressive the page cache, increasing it, more aggressive anonymous memory.
So, quick question: how many people expect, or their systems are swapping right now? Under normal operating conditions, they don't swap, right? Okay. So, I mean, the value of this would control whether or not you would actually swap a little bit sooner or later. But most people, once they see swapping, they get some kind of alert because the application is not satisfying its SLA, right? So you put some more RAM in there, or faster CPUs, something like that, right?
Okay. So the page cache caches file system data. The file system metadata is the on-disk metadata or file system specific data that is brought into memory and then cached. For instance, the inodes are cached, the dentries are cached, and several other data structures are cached. And in order to get that data, if you threw it out of the cache, you got to go back to disk. Well, in some cases, it's desirable to either have the system more or less aggressively reclaim that file system metadata. Specifically, something like the dentry. If you write an application, or you have an application running that does a whole bunch of what we call negative lookups. If you just have something and you do a wild card stat of like every possible file you can think of that doesn't exist on your system, down in the bowels of the file system, it's going to go out to disk and say, does this exist? No, it doesn't. And when it does the lookup to see, does this file system exist, it creates a directory entry for it and writes it into memory. So after a while, your system can be, the memory can be consumed by these metadata caches. And you'll see the TUND profiles sometimes adjust this VFS cache pressure. It's, the higher it is, the more aggressive the system reclaims this metadata. And then decreasing it makes it less aggressively reclaim the data. And less aggressively reclaiming it means it's going to use more memory to cache the data and then have to go out to disk less often to get it. We have something called min-free k-bytes. This is getting pretty low level here, but if you run vmstat on your system, you'll see free, the amount of free memory. The goal is to keep the free memory as low as possible, because below this what we call min, there are 3 watermarks in memory, high, low, and min. None of the memory is available to anybody below min, with the exception of some emergency kernel functions that take place. So if you went in and you said, I want to have a whole bunch of free memory, it's like removing memory from your system. You want the free list to be as small as possible. You want the operating system to use every page, every byte of memory that it can possibly use to cache as much information as you can get, so that you don't have to go out to disk as often. The downside of doing that, once again, this is a latency versus throughput issue. If make the system, if the system uses every last page of memory, it's got nothing for a buffer. What's going to happen when it finally does run out of memory, that operation that was taken 1 microsecond or something like that is going to trigger page reclaim and trigger all kinds of background operation so that the latency on some % of these high-profile operations might spike through the roof. So min-free kbytes is another one of these. It's rare that you'll see it go up by very much, but I just kind of showed what happened here. You can take and adjust the paging watermarks on your system with this min-free kbytes. Dirty background ratio and dirty background bytes. There are, let me just see. What I'm going to do here is just go forward quickly.
You go 2, 1 more. No, a couple more. There we go.
Yeah, that one right there. I'll go back in a minute here. So the way that the way that the background writing works is so the page cache is a file system data cache. When you do a write system call, all it does is take the contents of your buffer and copy it into a page of memory in the page cache and mark the page as dirty and count the number of dirty pages. So basically we don't do anything until we hit this background this dirty background ratio. We don't do anything. We don't flick anything out to disk on demand. The only thing that causes this memory to be written back to disk is Unix. The old Unix had something called an update daemon. And the update daemon would run every 30 seconds by default. And I'm sorry, it would run every 5 seconds by default and write out any page that was 30 seconds old or older. And we basically have the same provision inside of Linux. It's not called the update daemon. It's done as kernel threads and so forth. But that's the only way that the memory down below 0 and 10% dirty would get written out. And then if you overwhelm that, you just keep writing more and more aggressively, what happens is you go above this dirty background ratio, and every time you modify a page that pushes you above that ratio, it wakes up a background thread that will write the pages back to disk. It doesn't stop you from allocating or dirtying any more memory, but it'll wake up a background thread to flick things out. So that's the first level, or that's the second level of writing back. And then if you keep modifying pages faster than these background threads can write, you'll hit the dirty ratio, which is 20% by default. And what it'll do is it'll basically stop you, and it'll say you can't dirty up any more memory until you write some back out. The writing is asynchronous, so you can still go above that. But these two parameters together control the throughput and the latency of your write back. So if you raise these things up really high and didn't do anything, you're going to get massive throughput. You're just going to be able to write and write and write. But the problem is once you perform an operation that pushes you over the top, that is going to really stop the world, and it's going to sit there and write lots and lots of pages back out. So it would cause a higher latency. So increasing these increases your throughput and gives you your throughput and your latency, right? And lowering them does just the opposite. And with that, I think you want to go and talk about that.
Did you want to go back a slide?
Oh yeah, actually, I think I probably said.
I think you said more.
What I wanted to, anyways. This thing has a latency problem, so hold on. You got to tune it.
One more forward.
All right, so I think I said everything that was here controls that first low watermark, and then I think I said everything we wanted to say. Oh, the only thing I did want to say, we have a dirty background ratio and a dirty background bytes. It's a % of memory. So since memory is now potentially terabytes, 1% of a terabyte of memory is a lot. It's what, 10 gig, 10? Yeah.
100 gig.
So, yeah, 100 gigs. So it's very possible that doesn't give you the resolution that you want. So what we've done is we've added dirty background bytes if you want to go below 1% of memory, which is possible on large systems with terabytes of RAM. And the same thing is true with the dirty ratio. You have a dirty ratio, which is a percentage, or dirty bytes, which you actually can write a specific number of bytes in there if you so desire. We support officially, I don't know what our supported limit of memory is right now. I don't know if I want to. It's in terabytes, right? 16, yeah. So as you can see, that's a huge amount of memory, just 1% of that. And if you wanted to get lower than that, you'd use the bytes. So So.
Yeah, I mean, as Larry said, the tunedies tend to, so for like storage servers and stuff like that, we actually are bringing down some of the dirty ratios so that things get flushed to disk very, very aggressively, even for commodity storage. So
right.
As you go for more throughput, we can raise some of those. And again, the good news is it's tunable. There is one boot command that you can do to make things go very slow, and that's booting the debug kernel instead of the regular kernel. So just not to correct you, Larry, but so just please, debug obviously is there for full instrumentation, and a lot of the tools today don't need a debug kernel
right.
to operate on.
Yeah, we'll talk about that a little bit later.
So with that, we're going to let Jeremy take it over with networks.
Okay, before I get into that, two things I want to mention. One, when we started giving birth to RHEL 7, we realized there were several debug options enabled in Fedora that we turned off because they had too much of a performance impact. So we've gone through all of that. We've analyzed the config file for the kernel and decided what we wanted to end up with to provide comparative performance to RHEL 6 and in certain cases exceed RHEL 6. And then the second thing is that as it relates to storage, the write-back threads are now tunable in RHEL 7. So you can actually apply NUMA affinity, or you can apply CPU affinity to the write-back threads. That's not possible in RHEL 6. So if you have your applications running on certain cores and you don't want those background flusher threads to wake up and get scheduled on those same cores, you can apply affinity tuning to the write-back threads. So that is in the performance tuning guide. Third diversion. I'm told that in the last couple of days we pushed updated versions of all the RHEL 7 docs to the docs.reddit.com site, so the customer portal, to coincide with the release candidate that you'll get your hands on next week. Stuff we've been doing in networking in RHEL 7 as quickly as possible. Routing cache has been removed and replaced. The reason we did that is for determinism and scalability. Busy polling sockets. Massive performance increase. I'll show you some data. 40 gig NICs are supported as well. Also some data on that. VXLAN offload. I think unfortunately the slide did not make it, but we support that as well when the NIC supports it. And Network Manager now has a text-based and curses-based interface for configuring your network devices. So if you guys are familiar with the old school when you install, it would ask you for your IP address and netmask and all that stuff. You can do that through NMTUI utility in RHEL 7, and I don't think it was in the beta. So I think they took that feedback that they got from customers from the beta and built this tool. All of the talk so far has been about the effect of NUMA getting it right and wrong. And it's the same with networking. When you start going across the QPI links, things slow down. Sometimes it's an unavoidable situation if your memory consumes more than one NUMA node. If you can avoid it, you will get better performance. This is the ideal situation you'll most likely never reach, but this is conceptually what would be ideal. So what we've done to improve the situation in RHEL 7 is, well, actually in 6.4 it's in there, but IRQ balance now does NUMA affinity. It uses the slit table that we talked about earlier to provide hints to the kernel about what cores should process IRQs. And it does the same thing for storage devices. So IRQs from your RAID controller will be affined by default with NUMA in mind. So there's less and less to tune. If you combine that with the tuned profiles, out of the box, things are looking really, really good on RHEL 7. I'm not saying that you might not hit a corner case here or there. I'm sure you will. We'd love to have that feedback. But the reason we're delivering these profiles is because one size definitely does not fit all. So if you remember this slide from earlier, let's take a look at some of the two new networking profiles that are in RHEL 7, not in RHEL 6. You can easily move them over to RHEL 6, but they're not currently shipped. Network throughput and network latency. Right now, most of the gyrations are in the main profile. So these are children. I mentioned the inheritance concept earlier. And some folks are taking pictures or jotting things down. The slides are definitely going to be available, and the video. And also, Sanjay mentioned product limits. There's actually a product limit page on the customer portal as well. You can find out how much memory we support and how much size, you can scale an XFS volume to, and all that stuff. So unfortunately, I don't know off the top of my head. This is what a throughput performance profile does. Shaq showed you this earlier. Network throughput's just going to bump the buffers a little bit, and in reality, that actually has an impact on latency. We've told you not to do that for latency-sensitive use cases. For throughput, it turns out that there's a point where, and it's actually above 10 gigs. So unless you're using 40 gig NICs, the buffers you don't need to change. 10 gigs, you can do line rate without breaking a sweat on decent hardware in Linux with no MTU tuning and all that stuff. But for 40 gig NICs, it turns out you need to bump them a little bit, and it's actually a little bit less than 16 meg. We chose 16 meg as it's a nice power of 2, and that makes engineers happy. So the latency performance profile we hadn't talked about earlier. This guy goes one step further in stepping on the gas. It restricts the range of that the CPU idle driver is allowed to scale the processor C states. We haven't talked about power at all. There's a section coming up. This will lock the processors in C state 1, and by doing so, reduce jitter significantly. Do you guys remember that red line heartbeat slide I showed you earlier about latency with TuneD? That's all power. So in the default state, the processor is cycling in and out of these C states based on load. Every time it goes in and out, it takes amount of time for the processor's hardware to turn on and off various features. The amount is expressed in microseconds and is exposed in sysfs as well. Anyway, so the network latency profile takes the latency performance profile, all these different values. We're getting more aggressive with the write-back flushing. We're doing it more often so it doesn't have these huge bursts. Because what happens when you burst is that CPU is actually blocked, and any thread that's scheduled on that core won't run until the I/O completes. So we want to write more often. Faster storage helps in this case as well. Network latency profile itself disables transparent huge pages. Larry mentioned that earlier. We have some benchmarks and some customer feedback saying THP threads, the background, either it's compaction or even the scanning process itself needs to get scheduled at some point. It's the K huge page D kernel thread that can interrupt your app, right? And if you're not seeing any benefits from THP, like if you're already using static huge pages, it can cause some overhead and some jitter. So that's being turned off. The last 4 items are new for RHEL 7. You need support in the hardware for busy polling, which is currently IXGBE, MLX4, Mellanox, and Broadcom, and Chelseo. So those 4 NICs, if you have those, upstream Intel developed this busy polling feature, and what it does is it allows the user space socket to reach into the kernel, reach into the hardware receive queues on the NIC and pull the packets out. So it doesn't have to wait for a nappy interval, and it doesn't have to wait for an interrupt, which are the normal kernel methods for transferring packets from hardware to the socket, user space socket. So you can set a socket option, SO busy poll in your app, or you can do these thingamajigs over here in Netcore busy read and poll, which do it system-wide. There's a trade-off with power because it's spinning. So you'll see increased power when you enable those. That's why this network latency will never be the default, and neither will latency performance, because there's a measurable, and I have slides on it, I hope they made the deck, about the increased power draw when you start stepping on the gas like this. So when you floor it in your car, you get worse gas mileage. This is a similar analogy. The last thing is, second to last thing is TCP fast open, invented by Google, reduces 1 round trip for a TCP handshake by piggybacking some of the payload on top of the last SYN, on top of the ACK. So if you have a 50 millisecond round trip time, the total TCP handshake, instead of taking 150 milliseconds, now takes 100 milliseconds. So it's a massive improvement. For web-based workloads, we use Apache Benchmark on top of OpenShift, and it's a tangible benefit. Between that and power and busy polling, you can really, really boost your performance. So that's why these TuneD profiles exist. It's incredible. I think I showed you why do I care about this slide in the first deck. It's 15%, sometimes more. And there's some really good stats coming up about busy poll specifically. So the last thing is NUMA balancing. Right now, so we talked a ton about this auto NUMA balance code in the kernel for RHEL 7. It's on by default. In the latency performance, network latency tuning world, you kind of want to not have the kernel moving stuff around unless you really tell it to do so. And so we're disabling that for now. That's the way it's going to be in GA. We're going to reevaluate that one very closely because there's active development going on upstream about it. the end of this deck, there's a slide that shows you where what time the Rick Van Riel's NUMA balancing talk is. I think it's later in the afternoon.
Yeah, it's after this one. Yeah.
All right, I talked through most of this guy. You want to evaluate these profiles. No one's dictating anything, so you're gonna flip these on and off and just measure your performance before and after. There are some kind of basic guidelines. HP and Dell all ship performance, or maybe if they call it low latency, performance tuning guides for their BIOS. You want to follow those best practices. Turbo may or may not get you a boost, so you want to do A/B comparisons on and off for these features. I know it's a lot of work. But that's how you'll come to the optimal performance for your application. File system journal, some people want to use ext2. You can do that just fine. Faster disk helps those writer threads get blocked for less, those cores that are processing write back get blocked for a shorter period of time, so faster disks always helps. And NIC offloads are a huge help. I mentioned VXLAN offload, so Mellanox sells a NIC that does VXLAN offload, which boosts performance like a huge amount. I think it was like 15%. One of my coworkers tested that very recently, so got a 15% performance boost on a 40 gig NIC in an OpenStack environment. One of the attendees mentioned, was asking me about kernel buffers. This is the SS tool. If you're not familiar with it, you probably should get familiar with it because netstat is shipped, although deprecated in RHEL 7. So you won't get it in a default install. You have to install the NetTools package if you want to rely on that crutch for RHEL 7. But the development is all in the SS tool, which isn't part of the IP route package. Anyway, it shows you a lot of similar information, including all the socket options that were used, so you can verify if you've got TCP no delay set on the socket, or if you've got this busy poll socket, or a set sock opt call if your application is doing something like that as well. You'd see it in the SS tool. It also tells you what the arrow is pointing to now is the buffer queue depth of the kernel. This is a 10 gig TCP stream between two servers. The buffer never gets above 4 megabytes, so, and it's line rate at that point. I don't have a graph for 40 gig, but the buffer is about the same. It gets actually to about 5 megs on a 40 gig stream, which is pretty good. Here's the NUMA I got it right versus NUMA I got it wrong slide. 40 gig NIC between two Sandy Bridge machines. If you get it wrong, you only get half speed. So if you get it right, you get line rate. And you want to make sure that, using some of the, I have a slide at the end that's going to show you a bunch of tools. I think Shaq put it at the end of the first part of this conversation. Same slide's coming up. NUMA Top from Intel, Intel PCM tool, and also NumaStat will show you hits and misses on each NUMA node. So Intel PCM actually, at least as far as I know, is the only way to measure the QPI link traffic, so the interprocessor link that Larry was talking about earlier. The groups of columns are different TuneD profiles, so if you're looking for 40 gig, you're going to want to use, most likely you're going to want to use the network throughput profile. And if you can, jumbo frames. You can see there's a huge hit without jumbo frames. We're bottlenecked on the CPU at that point. If I had Haswell or Ivy Bridge, that number would have been higher. This is a Sandy Bridge system. Daniel Borkman, who works for the network engineering team at Red Hat, wrote this NetSniff package, which was never in RHEL. And now it's in RHEL 7. It's in Apple for RHEL 6. It has a visualization tool called IFPPS in it, which consolidates a bunch of system-level statistics. I don't know of a better way to consolidate network and performance analysis than this tool. It also has a CSV mode. If you want to dump it to a file while your benchmark is running, that's cool. I tend to use it all the time because it does something no other tool that I know of does, is it shows you the soft IRQs as well as the hard IRQs and what processor is processing the top half and bottom half of the interrupt. So packets a second, drops per second if there happen to be any. This thing is slow. Hard and soft IRQs, and so IFPPS. It's part of the NetSniff NG package. He also has a TrafGen tool if you want to generate traffic really, really fast as well in that same package. Okay. So TCP tuning, we have the no delay socket option. If you're not familiar with TCP no delay, it's called, you may have heard of the Nagel algorithm. Basically, the sender will wait until it has a full MTU size of data on the ready to transmit before it actually dispatches the packet onto the NIC. Nagling disables that waiting period, and just as soon as the application sends it to the kernel, it puts it right on the wire. So it tends to reduce latency quite a bit. TCP low latency, I actually found like a half a microsecond benefit, so I tend to that's really not a big win. NUMA, as you saw, is a huge win. Kernel buffers are right-sized. That's kind of why we're trying to deliver these tuned profiles. So you don't have to guess at this stuff anymore. At least you can use our profiles, which are standard in RHEL. You can use Puppet or Chef to lay down the configs and not mess with anything by hand anymore, we hope. And setSockOpt can adjust those buffers on a per socket basis. Your application may be calling it and reducing performance if they're setting it too low. On the UDP side, there's several knobs. You want to make sure, again, network throughput bumps the buffers, the UDP buffers as well as the TCP buffers. There's several knobs in the kernel, again, about the number of outstanding packets that can exist at any given time. ETH tool will help you set ring buffer sizes on the NIC or interrupt coalescing times, and certain NICs provide a different level of functionality than others. So I didn't include any snapshots because your mileage may vary based on what NIC and what defaults that they choose. Some NICs wait 60 microseconds between doing anything, doesn't matter how many interrupts it gets, or some people do it on every interrupt. So you kind of got to look at ETH tool minus C to find out what your network cards are set to by default. There's also a drop watch tool in RHEL 6 and RHEL 7, which can, if you're dropping packets, it'll tell you what kernel function the packet was dropped in. If the drops occur in firmware in ETH tool, if the drops occur in firmware, you'll only ever see it in ETH tool because it happens outside of the OS's point of view. Okay, who's aware of what the kernel timer tick is? Local interrupts? Just a small handful. I'm going to go really quick through these slides because it's kind of a niche optimization, but it was a massive amount of work by several companies in the space of real-time embedded, but it's actually in upstream and in RHEL 7. So I do want to mention it because it's a big feature for RHEL 7 for certain customers. So the kernel in RHEL 5 ticks 1,000 times a second on every core, no matter what. In RHEL 6, we have the tickless kernel, which was invented to save power. It shuts those ticks down on idle cores. It still ticks 1,000 times a second on active cores. In RHEL 7, it's the same tick behavior by default as RHEL 6, so still 1,000 hertz. And we also have an optional opt-in feature called fold-in ticks, which will allow you to disable the kernel timer tick on certain cores, even when they're active. There's a little nit about it that you have to have only one thread scheduled on that core. So the number running would be 1, otherwise you fall back to the normal mode. And most customers are seeing 1 or 3% performance improvement for HPC type workloads, for embedded type workloads with response time requirements and financial guys. So Red Hat collaborated with IBM to develop this feature, and it's been upstream for several months. We're iterating on it still, but it's actually given us, I've gotten good feedback at the summit about it. I kind of went through these slides, and so this is RHEL 6 and RHEL 7 by default. Left to right is time, so there's the vertical bars or the vertical gray bars are actually timer ticks, and where the X's are where the tick is disabled because of the tickless kernel. So that's an idle. When it's blue, it's idle. Those ticks don't occur on those cores. When you enable this fold-in ticks feature, you don't get any ticks. So it can help improve performance 1 or 3%. Okay, busy polling. I mentioned this a little bit earlier about how it reaches into the hardware's receive queue and pulls packets out. So I kind of jumped ahead a little bit. What's great about this is it's a massive latency improvement, but still retains all the features of the Linux kernel stack. So TCP dump, all the statistics that might populate in SS. Instead of, you lose a lot when you start using bypass technologies like either RDMA or certain other bypass technologies, maybe for Ethernet. They don't go through the network stack, and so the kernel never sees those packets, and so there's no stats. You're actually relying on the vendor to provide equivalent stats or functionality like TCP dump. This is an Intel NIC, and like I said, Intel invented this feature. So they, on the left-hand side, this is default. This is a ping-pong netperf TCP and UDP latency test. So it sends one packet, and it reflects it off a user space off the other machine, and counts how many times it can do that per second. So on the left-hand side, you see we're about 35,000 transactions per second. That's ping-pongs per second. You enable this busy polling, and you're almost 2x. So it's a massive improvement for this type of workload. If you have a latency-sensitive workload, like a web-based transactions, you might see a big boost. And like I said, it requires driver enablement. It's not going to be in the GA, but we already added to ethtool support to query the NIC to see if this feature is supported on your hardware. So I apologize, it's not in the GA, but we already have it in. We already have it upstream. For now, you just have to I'll just let you know by verbally. It was actually in the performance tuning guide. We put it in there. Okay.
So Jeremy, just before you keep cruising on too long, so for UDP traffic, which people are trying to basically send and receive essentially without TCP and keep things balanced. So which profile, the network latency or the network throughput? And or are there other tunings?
It depends. You might not need a profile at all. You might get away with the default profile. If you're trying to push the limits, I would say the network throughput profile probably suits UDP better because it gives you a little bit more buffer size, and that's actually just a safety net. So if your application is slow to pull things out off the wire on the receiving side, it'll allow more space on the sending side to queue those packets while the receiver catches up. So I would say we normally, when people are seeing UDP drops, one of the things people tend to do is increase these buffers a little bit. You need to use SS before you blindly increase those buffers to see if that's even the problem. It could be something else entirely.
Thanks.
Okay, so I mentioned C states earlier. That's a power saving mechanism. P states are the frequency scaling that existed for so long in Intel chips, and it's the CPU speed service on RHEL 6. So that's the definition of those. In RHEL 7, we have a new driver called Intel P state, which really threw us for a loop when we first saw it. We have a really good understanding of it now. We have an excellent relationship with Intel and constant dialogue with their power management developers. So it's all sorted out in the GA product, which is I'm thankful to say. One of the things we did is they've decided to move away from the concept of CPU governors in newer chips. And they're moving to this knob called minimum and maximum perf percentage. So the floor is the minimum. And in all the performance profiles, we're just bumping that up to 100. So you'll have 100. It still actually doesn't mean the frequencies are locked at the highest. It just means, like Shaq said, the aggressiveness of the CPU to move to its faster frequency. It also gives us the ability to turn on and off turbo from user space, which just makes, at least for me, makes testing a little bit easier. And we've also got this. So in RHEL 6, we have this MSR in the, a register on the CPU that was programmed at performance by default in RHEL 6. We inadvertently turned that off in RHEL 6 in an internal build, and our QA immediately caught that. So it's back to performance in RHEL 6. In RHEL 7, since we adopt from upstream, it's actually set to normal by default. And there's a little bit of a hit there, so in the performance profiles, we're dialing it back up to performance. So it was Intel's decision to change it to normal, and we're kind of saying what's right for the data center seems to be performance. And again, these are all tunable. You can change them all on your own. I mentioned CPU consumption based on power. So if you lock the C states using the network latency profile or the latency performance profile, you get a 5 up to a 25, almost a 30% increase in power draw for certain workloads. So this is what you're paying for the extra performance. It doesn't come for free. There's a tool called Turbostat in RHEL 6.4 in the CPU power utils package, or in kernel tools package in RHEL 7, and it can tell you what C states and frequencies all your cores are at. It's a great debugging tool to find out if you're hitting any of these power problems that we're talking about. I think one of the last things I want to mention is about turbo. It's actually defined in hardware. The algorithm is actually defined on the CPU hardware, so you're not able to adjust this, but I wanted to show you what the testing looks like. If you have one busy thread, you get a huge boost in frequency. Let's say your chip is 2.9 gigahertz by default. You can get a boost of 800 or 900 megahertz on a single thread. But the more busy threads you have, the less that boost is. So that's what the left to right is here. If you have 8 busy threads, you're getting almost no boost. But if you only have one busy thread, you're getting it's actually a 700 megahertz boost on this chip. So that's something to be aware of. If you have a highly threaded workload, your CPUs will not be running at a higher frequency. So, all right, Larry or Shaq.
Yeah, thanks, Jeremy. And as you can see, the network scope and a lot of that was some of the new features in 7. Very wide space, covering everything. Jeremy is a guru, low latency, rocket science type of both person and working with the kernel guys to deliver that in RHEL. So if you need to do follow-ups, we definitely work with a lot of ultra latency sensitive. Network throughput, quite frankly, is probably a good start for most loads when you're network centric. Otherwise, our other TuneDs should work pretty well. So we're going to switch gears now and go through some of the performance tools. Again, this is some of the more recent ones. Performance Copilot, again, was derived and still is founded with SGI's system. We're using that for multi-systems, and quite frankly, we're using it in a lot of our cloud and scale-out systems like Cluster, etc. So when we can plot things together, we can make more sense of the statistics. A couple README on, a short README on how to either use. So the beauty of these tools, much like SAR, you can record your performance to a file and then be able to replay the file. And so, especially for long-running, IT shops, you may have other third-party tools that do this for years. So we're not trying to necessarily compete in that business, but we are trying to ship things with RHEL, with our distribution, for when it makes sense. And so again, you can record Copilot using this command, and then you can then plot. So one of the things I think they actually just said, we're also going to put this in the RHEL 6 environment too. It's in 6.5 under the Apple packages. But we're really trying to find the first order of magnitude of performance problems. So CPU, network, we're looking at I/O and memory consumption, and we're trying to avoid some of the pitfalls that we shared with you in the past. So this is a good quick example. It uses a tool that ships, all these tools ship in RHEL, whether it's netperf or DD to do disk I/O. Netperf stress actually can be used to artificial workload, but to basically put load on memory and CPU. And so you can specify things on both thread counts and or the number of bytes, etc. And so a quick sample of output here for you is you can plot it over time. If you do it for a month, you don't necessarily need, you can actually change the interval of the resolution that you're looking at. You can plot multiple systems, so visually see things, kind of correlate events to when a catastrophe happens. Let's go back through the the IOP load. Obviously, when we did the DD load, there's a spike here, and it tells you the metric. And usually two things, and it sounds like a broken record, throughput or latency. So how wide is the highway, and how fast is the speed limit, right? Latency is how fast, and can you respond actually quickly, where how many lanes in the highway, how much stuff can you get through the highway is the throughput. Same thing for network, and then in the bottom you're going to see the stress tool ramp up to use more and more memory till it gets to the peak, and then when the process exits, the memory drops to its current values. So there's, again, plenty of other tools. We've talked about SAR. Here's another one called, it's actually, this is integrated with Copilot, and it's called PM collectal mode. So it actually displays things like collectal in terms of its output. CPU, context switch categories, correlated on the same lines, on the same chart with IOPS, so IOs per second versus megabytes a second, versus network versus disk IO versus memory consumption. So you can get these pictures rather than, for VM you got to run VMstat, and for network you got to go SAR dash and dev slash, etc. So then really like being able to correlate these together so you get the unified view of what's going on. Let's see, on the there's another another tool that, again, runs in this RHEL 7 only or 6.5 as well?
No.
I think this is 7 only, but it's ATOP, again, sharing both CPU. A lot of times when you do CPU, you do need to break it out on a per CPU basis, because if you have a single process job that's saturating, the aggregate CPU is not sufficient. Similar on network and disk I/O. So our tool set's getting richer. Doesn't mean your older tools are deprecated. In fact, the interfaces are still common. So current tools that get used for these data centers are not only going to continue, but they're probably going to no change needed, and just a little bit of a certification process that happens when we move from major releases between like Red Hat 6 and Red Hat 7. Back to Jeremy.
I'm going to burn through these because I want to make sure Larry has time for perf, which is probably the most exciting tool. We did add some features to Tuna for RHEL 7. This is stuff from last year where you can kind of do all this stuff on the command line. This is setting affinity for IRQs on the command line. Again, slides all available on the customer portal in a couple of days. Customers asked us that we're using Tuna, how do you, if there's a GUI to it, there's always been a GUI, but it never had the ability to save stuff that you had experimented with, and the GUI had to save it to a file. So we've added that for RHEL 7. It's kind of an exciting feature. So this is what the GUI currently looks like right here. You've got CPUs in the top left, IRQs in the right, threads in the bottom. That's what's been in RHEL 6 and in Merge for the longest time. These are new tabs. You can now, so does these look familiar? These are a lot of the knobs that we're adjusting in TuneD. And you can drag these sliders left and right, turn these features on and off on the fly with this tool, save it to a file, and then replay that file later using the command line. And you can also edit it as plain text, the profile. That is a duplicate slide. That's what it looks like when you do the Tuna IRQ affinity. I apologize, these slides somehow got jumbled. But so because SolarFlare and Intel, everyone ships their own IRQ. Mellanox also, they all ship their IRQ affinity scripts with them. But Tuna can replace them all. It's also NIC agnostic, and it ships with the OS, so it's a lot nicer to have one tool to rule them all. Tuna can do process affinity, and it can do socket isolation. One customer asked me about ISIL CPUs versus Tuna, and in fact, you can do it all from user space instead of using ISIL CPUs on the kernel command line and save yourself some reboots. So Tuna will adjust the runnable CPU allowed list based on what isolation socket, isolation parameters you've passed to it. And we do have some time for perf, sir.
So one of the tools that we use in profiling the kernel and figuring out when we run into problems with high system time, or even if it's not high system time, just to find out where the system is hanging out, is a tool called perf. It's available in RHEL 6, and it's embellished even more in RHEL 7, lots of different features. Over time, sort of the profiling of the kernel has undergone quite a bit of upgrade. Years ago, there was a file in proc called profile, and basically what happened is every time the clock interrupt service routine went off, or the tick, it would look at the PC, the program counter, and if it was inside the kernel, it would basically figure out a bucket to increment, and it would just simply increment the counter. And then you could run a tool called read profile that would take the kernel symbol table and that list, and it would just tell you basically where the system was spending its time. The downside is it required the clock interrupt service routine to go off all the time. So if you disabled interrupts, it was either didn't work or was inaccurate, or the routine that would show up all the time would be the routine right after the clear interrupts. So this perf is a user space tool, and it reads CPU counters. The CPU counters are new counters, most of them new counters, and trace points that we build into the kernel. So running perf, do we have people here who use perf? Okay, there's some experience with it. So you can do a perf list and list all the different counters and trace points available on your system. You can grep for different things, so if you want to look at various NUMA things, you can do that. If you run, let's see, what we got right here. This is, I think, a perf top. Yeah, perf. So if you run perf space top, It runs like top. It'll tell you in this case right here, 34.35% of the time was spent in this routine, and it tells you exactly where you're spending your time. If it's the kernel or some module or your own address space or whatever, very useful in telling where you're hanging out. There's a feature called perf record. It's system-wide with a -A, single command for an existing process with a -P option. You can add call chain recording, and I'll show you what that is in just a minute with a -G. And then you can isolate specific events. And then in this case right here, Jeremy, I think you put this together, we're doing a perf record of a DD -G, so this is going to be call chain recording. And we're going to go, the in file is dev0. So in this case right here, it'll break down exactly what % of the time is being spent in each routine, and then the routines that are actually called from that. So it'll actually build you a call graph to tell you exactly where you're hanging out. This is really useful in terms of debugging a problem that's going on, finding hot spin locks, and finding problems associated with NUMA placement issues. These, obviously, if it's doing a lot of cross-memory references or taking spin locks on other nodes, then these things are going to bubble themselves up higher, which is a good time to talk quickly about Joe's.
Yeah, so again, an extension to this that's coming out in 7.1 is a cache-to-cache analysis tool that takes the same methodology, uses newer counters and now have a bridge, and basically allows you to it has to do backmap virtual addresses to physical addresses, and then look at the Intel cache lines and see where you might be contending on the physical cache lines. So you'll probably just see high either user time or system time. The perf tool will show you where it's happening. The cache-to-cache tool shows you who caused it, not just what happened after the fact.
Right.
So
they're giving
very cool.
But there's a presentation in the dev nation.
There's a presentation tomorrow, and I think we have a list of presentations that we are going to wrap with in about 32.5 seconds.
Okay. So the perf also allows you to do a diff. So if you basically do a perf, I think this is using record. You can, and then you make a change. You can see what the differences are in terms of the % of time spent in different areas.
Jeremy did this one and essentially evaporated all but like 0.6%.
So the negative number, it was a 12.88. We dropped it by 12.88. So essentially that was Alviro who fixed something for us. Dropped it completely off the profile, this contention for the lookup mount function.
And then finally, you can use the dynamic trace points in the kernel and be able to record. Do you want to say any more about this, Jeremy? Or
well, so perf list shows you everything that's in the CPU and everything that's in the kernel. There's also, you can also trace arbitrary functions. Perf probe -f dumps out thousands that you can insert your own trace points.
Do you want to take this then?
Sure. And so as usual, we've sucked down every minute that they gave us and probably half the oxygen in the room. So we were happy. We do see quite a few entries on the tablet. We're going to take them either outside if it's not too busy, or else we're going to go into like the demo area. And in summary, there's a lot of tuning that can be done. We think most of it is happening automatic. But if you guys want to do further optimize, the reason we get excited about 12–15% is our team gets paid in buffalo wings, so every percentage is one buffalo wing. So the 12%, 15% that Jeremy's like, this is awesome. It's also good and fun. So
he's not kidding, by the way.
Incite your teams to pay them off in buffalo wings, and just be careful. In cloud, they're getting factors of 10, 100 improvements, so it's getting a little scary, and all the chickens in Delaware are nervous. Thank you again.